Alrighty, let's go to the next bit problem today. Bitwise ORs of subarrays. Given an integer array R, return the number of distinct bitwise ORs of all the non-empty subarrays of the array. The bitwise OR of a subarray is the bitwise OR of each integer in the subarray. The bitwise OR of a subarray of one integer is that integer. Subarray is contiguous, non-empty sequence of elements within an array. Return the number of distinct bitwise sub-ORs of all non-empty subarrays. Non-empty, okay. Number distinct. So this is obviously just one. 1 and 2 and 3 are the distinct values you can get. Yeah, 1, 2, and 3. It's 1, 2, 6, and 7. 1, 2, 4 is that's 3. Then this is 3, 6, and 7. So there's 6. Okay. Interesting. Answer equals 0. Can I do? Nice. I'm thinking if I can do a set of values and then count the set. Would that work? It would have to be, if I do the set of values and count the set, I probably would be, that probably implies that I'm trying to go through every possible set, possible subarray to get the bitwise orb, the subarray to add to the set, where if it's 5 times 10 to the 4th, if I go through all possible subarrays, it's probably like n squared. So that's probably not it. So probably, yeah, so I think I should, yeah, I think I should sort it. At the very least, I should just find the unique values in the array, because the unique values in the array are not going to, it doesn't really matter. No, wait, it's a subarray, so the order does matter. Alright, so if the order matters, I guess you could probably like move the streaks of values. If there's like a 1 and a 1, that doesn't really change the possible combinations you can get. So you can at least ignore that part. What else could you do? 1, 2, 4. Could you do some sort of sliding window? So 1 is unique, and then you open up to slide the window out to 2. That gives you 3 is the bitwise OR of that. So that's added to the unique set. And then we can't really close the window because the 4 would need to be added to the window. That gives you 7. But 2 by itself should be 1, and 2, 4 should be another one. Bitwise OR. 1, 2, 4, 1, 2, 2, 4, 1, 2, 4. Yes. So every value in the array should be added to the set. I guess I could do that thing that I did a couple of days ago, where I count the number times a certain bit appears within some window, and if it let me think. So if I were to add an element where the bitwise OR doesn't change, if I were to add an element where the bitwise OR doesn't change, then what? If I add 1 and then another 1, then I could remove the 1 from the left side of the window as part of the subarray. The number, return the number distinct bitwise OR. So how do you know? So if you do 1 and then you add the 2, it becomes 3. So how do you know that you can remove 1 and get a distinct 1? Every extra value. So if you do a bitwise OR, the value always increases. So do you use 1 increases to 3 when you do bitwise OR with 2. And then that increases to 4 when you do bitwise, or it increases to 7 when you do bitwise ORs 4. So if you don't, so if you do something where, let's say, it's 1, 2, 4, 3. So you do 1, 2, 4. If you extend out to 3, and that doesn't increase the bitwise OR, each value itself should be added to the uniques that you can get. Each value itself should be as part of the uniques. So the question is, how do you count the combinations from subarrays that are more than 1? 1, 2, 1, 2, 4, 4, 3. 1, 2, 2, 4, 4, 3. N squared? N squared subarrays. Yeah, N squared I think is just too big. One, two, 2, 4, 4, 3. So we do 1 and 2. If you do 1 and 2, you get 3. So this becomes 3, 4, 3. But if you don't do 1, 2 combined, then it should, in theory, also be 6. So 2, 4 becomes 6. And the 3, 4 doesn't actually have that. 1, 2, so yeah, I really can't simplify it. As in, I can't combine 2 adjacent ones and say that they're going to be treated as the bitwise OR of the. I extend out the window. 1 extends out to 2. The number of distinct bitwise or all non-empty subarrays. There's n squared non-empty subarrays, or like n squared over 2 approximately. How do you quickly iterate over all possible? One, two, four. 1, 2, 4. If you do 1 bitwise or 2, you get 3. And then what? So you can either treat it as 3 bitwise ORed with 4, or just 2 bitwise ORed with 4. Alright, I think that. So that's the only combinations we can do. If you do 3 bitwise OR with 4, that gets you 7. So the 4 can either become a 7. The 4 can remain a 4, or it can combine with the things that are preceding it, the different values that can be preceding it on the left, which in this case is only 2 and 3 are the unique values that can precede it. So if it combines with a 3, then that makes 7. If it combines with the 4, or combines with the 3, that makes 7. Combines with the 2, that makes 6. Or remains 4, and that's that. Yeeks. That seems like a lot of combinations. But I mean, that is the possibilities, I guess. There's no other possibilities at that point. So the 1, 2, I guess maybe, yeah. 1, 2 combines with 3. 3, 4 combines with 7. 2, 4 becomes 6. Or nothing is 4. And then 7, 3 becomes 7. 6, 3 is 6, 3 is going to give you 6 is 4, 6 is 4, 2, so 6, 3 combines with 7. 6, 3 combines to 7, and then 4, 3 combines to 4 is 1, 0, 0, 3 is 1, 1, so 4, 3 combines to 7 as well. So the options there would be 7 or 3 at that point. I think. For yeah, That's right. 4, 3 combined to 7. Anything past that combines. I mean, 7 is going to combine with anything smaller than 7 to be the 7 itself again. I don't know if this is... I mean... hmm. One, so you start with 1, bitwise or 2. You either get 3 if you do that, or if you don't choose to have the 1, you have 2. At any given point, you have like how many possible values to start with. It's gonna be at most the max value of n of any value. Oh shit. That's 10 to the 30, 10 to the 9th, so 32-bit value pretty much. So there's a lot of possible values that you can start with. Can you simplify that somehow? Boo, boo, boo. 1, 2. Buckle a shoe. 1, 2. If you start with I mean, we have some unique set of values that you have on the left side that combine with your next value. The number of uniques that you can have would be the number of uniques that you have. So a bitwise or any subarray is going to be larger, at most the largest value in that subarray. No, that's not right. For any subarray, the bitwise OR would be at most bitwise OR of the overall array. So I mean, it's capped to be 10 to the 9th, I guess. Does that help at all? 1, 2, 4. Okay, let's do another trial run. Let's say it's like 5, 5, 3, 1, 2, 4. So you start with 5. 5 is 4, 1. So then the next one could be 5, 3. So 5, 3 gets you 8. No, does it get you 8? 5, 3 gets you 7. No. 4 plus 1 plus 2. Yeah, I guess it gives you 7. So it could be 7 or 3. So it's like 5 next to 3, then 5. It could be 7 next to the 1, or 3 next to the 1. And then 7 and 1 gives you another 7 next to the 2. 3 next to the 1 gives you possibly 3 next to the 2, and then we go back to the 1 next to the 2. 7 with 2, well, 7 with 2 is just going to be 7. With the 4, 3 with 2 gives you 3 with the 4. 1 with the 2 gives you 2 with the 4. And yeah. And then you get 7. 3 with the 4 gives you 7 again. 2 and the 4 gives you 6. So in the end, you get all 1 through 7 as possible values. That seems too slow. I mean, yeah, it seems too slow. 1, 2, 4. Where are the stuff that is like redundant or like can skip some calculation? If you add an element to a bitwise OR chain, like how do you know that maybe you don't need to do that calculation? Besides, like when you do a repeat value. 7, 3, 1 is next to the 2. Even if it's a smaller value, you still have, unless it's like a smaller value XORed with something that has all the bits on, does change the value. 3 XORed with 2 gives you 3. That was like 4 XORed with 2 gives you 6. Alright, what if I kept track of the bits, does it help me? So 3, 5, I have a bit at the 4, a bit at the 1s. And then 3 has a bit at the 1 and 2. So that window becomes like 1, 4, 1, 2, 2 1s. Huh. Every possible subarray XOR. Every possible subarray XOR. I wonder. I wonder if you can treat it like a tree, where you either choose to combine adjacent stuff. Aw. 3, 5, 3, 1, 2, 4. So you have 2 nodes that are 5 and 3. They have an XOR value of 7. 5, 4, 1, 2, 1. The XOR value of 7. So you can treat the parent node of 5, 3 as either 7 or 3, I guess. Seven or 3. And then the XOR, if you treat it as 7, XOR 7, 1 is 7. Treat it as a 3, the XOR value of 3 and 1 is 3. Yeah, the node just has an array of stuff. Where the array of stuff is this thing ready. I mean, maybe that's still the only way to do it. No, it's just the fact that, yeah, maybe, yeah. Alright, that's, I don't know. I guess I can try it. For every value in, let's say possible is a set, and every value, actually maybe this needs to start with, with the first value. Array at 0 for every value in an array after that. So actually let's call this uniques. Possible is another set at each stage, each value. For each unique, no. I guess I need to actually start with left. Yeah. Maybe previous values is initially a set like that. Uniques probably start with array of 0 as well. Combine is a set for every previous values, for every previous and previous values. Combine dot add the previous value XOR with the current value. Same thing with uniques dot add this value. I guess maybe I can call this combos. And the current combo is previous XORed with this value. What the heck? The combos would include this. And the Unix would include this combo. And I guess now I would say the previous values, pre-values is equal to combos here. And I return the number of uniques. Alright, I mean this is n squared almost certainly, but every value, previous and previous values. Oops. Pre-values. Combos.add combo. It's a dictionary. Oh, whoops. Python is kind of weird because sets you can kind of statically define a set using curly braces, but you can't define it using an empty set using curly braces. Uniques.add combo. Oh boy, that's not good. 2, 4. Really? Oh, it needs to include itself. Okay, actually, there's a couple of things I need to change. One is to not do repeats for index and value in enumerate array after the first element. Val equals nums or array at this index. And I think, okay, so set, and if the value here is equal to the previous value, so array index minus 1, continue. Combos, otherwise needs to start with possibly including this value. Still wrong. Interesting. Okay, so unique start with 1, previous value start with 1, every index starting with 1. Oh shit. So index here will start with 0. So I think maybe I should just do for every index in range 1 to n, where n is the length of the array. Yeah. Still wrong. Huh. So if index is 1, the value of 1 is going to be, value of array index 1 is 1. That equals array index 0, so that's fine. Combos, oh, okay. Value combos, maybe I should start with uniques being the set things in the array. That's probably a better starting point. Okay. Okay. Too slow, too slow. Oh my god. Really? That's not too slow. I mean, they're I mean, this is ahead of the curve, but then there's something much faster. Okay, let's consider this. Alright, I really need to think of something a lot better than this. Okay. How do you improve this? Identify redundant calculations, I think. 1, 2, 4, 3. Where's the redundant calculations found? Or how do you know that you can skip something? So if you go to a number, so if you have a set of numbers that are unique for the previous value, and you have a new number, like if you saw that number before, is it possible to ignore it? Or if the number XORed with the previous value doesn't change the previous value? You can't really sort it as much as you'd like. Can you sort it? I don't think you can sort it. Like the 1, 2, 4, I think you get different values. So it's like 1, 4, 2. Yeah, like 5. Yeah, 1, 1, 4, 2 gives you 5 at some point. 1, 2, 4. 1 combines with 2 to get you 3. If a value in your previous set So combos.add this combo. I think maybe I can do, instead of adding each time like this, maybe it's better if I did something like uniques dot, I think it's update with the combos. It's like a smaller set of things that you need to worry about. Okay, I think that's a slight improvement. Within margin of error, so I mean I think that's within margin of error, so maybe it's not any improvement. Nice beating percentage. The memory and the runtime is equivalently nice. When you do the if values the same, that gives you some degree of thing of optimization. If value, is there something else that you could skip? If value is less than, can you skip? 1, 2, 1, can you skip 1? Or if it's like something that strictly doesn't have any difference in bits. So every previous value, the combination. I guess I can just do without this thing here. this previous value XORed with the current value. I guess maybe, no, I think I have to do that. Yeah. Previous values, combos starting with this one. Yeah. Guess that's removing one kind of assignment. Oh my god, 96% using that one change. I'm tempted to actually just click on this and see what the actual fastest solution might be. Alright, but I think this is good enough. I guess my understanding for it was decent, or the solution for it was decent. Okay, so I guess the example summary, example application of what am I trying to say here? And this is example understanding algorithm. So let's say the array is 1, 1, 2, 4, 3. So this is going to, for each value, keep track of all possible resulting combination, keep track of set of possible resulting combos of that value and the current value and the next value. And then use that set to use that set as possible left side combo values for later iteration. So if it starts with 1, then 1 XOR with 2 gives you 3. So the set is, the combo set would be 3 and 2. And then 3, at that point the 1 and 2 is done, giving you either 3 or 2 at that point. So if it's 3 XORed with 4, that gives you 7. If it's 2 XORed with 4, that gives you 6. So the set there would be 7, 6, and 4, because you can do nothing as a possibility of combining. And then 7 XORed with the last element in the array, which is 3, gives you 7. 7 XORed with or 6 XORed with the last element in the array gives you 7. And then 4 XORed with 3 gives you 7. So the combos at the very end would be like 7 and 3. If there were more elements there, like let's say there was like 12 here, then the 7 and 3 would combine with the 12. So on and so forth. and then yeah, so that's primary. Yeah, that's primarily what the algorithm's doing. So so overall, this is going to be keep track of all possible left side combinations that can be formed. Iterating that set each time. Keep track of an overall set of uniques that have been encountered, and return the count of those uniques. So you start with a base set, which is every unique value in the array. Your previous value you just assume is going to be your first value, and then iterating from the next one onwards. The value at the index, technically if it repeats the value from the previous stuff, it doesn't actually generate anything new, so just skip it. But assuming it's different, then say the combos that can be formed from the previous value with this current value. Well, one is that you can ignore everything previously done, so you can just say this value is there. But otherwise, for every previous value, then do the bitwise OR that previous value and this value adds the current combos. After that's done, update the uniques. This is adding a set with a set, and then whatever the current combos that you have, those become the previous values for the next iteration, and then return the length. Alright, time complexity. Oh, this is kind of I want to say this is close to n squared, but it's not quite n squared. It's like n something. O of nk, where n is the length of the array, and k is the average size of combos at any point in the array. But what is k? Is k... K is at most n? No. K is at most what? Average size of the combinations, of previous combinations. Previous combos. Because the iteration is for every previous value that you're doing the bitwise OR with the current value. That's the inner for loop. I guess that could be n squared, but this thing was pretty darn fast. This was 367 milliseconds. I'm not sure actually. This is very, very weird in terms of being different than other types of problems I've seen. Generally, they're much more. I guess for me, other problems are much easier to define how quickly they go through things. Yeah, I'm gonna say this is correct, but I think there should be a better someone smarter than I can define this better. Space complexity is going to be O of how many uniques could there possibly be? Because you're keeping track of the uniques, right? So, well, the uniques. You need to keep track of the uniques. Like, there's just no way around it. So, I mean, it's not like you're keeping track of things that are unnecessary, but the size of the answer, like even if there are n things, there could be n things. In theory, it could be as much as n squared, maybe. Um, uh, proportional to the overall number of uniques that would be counted, because every unique that's there is at some point part of the combos, and at some point, and at the very end, part of the set of uniques. So I think it's n squared. Yeah, I could be definitely very wrong with that. Not confident. Okay.